IQS. Thank you, Malina. Welcome everyone to our installment of our lovely seminar, IQS seminar. Today we have Ahmed Hajr. He's according to his own website, he's a fifth-year PhD student in applied science and technology, working in quantum nanoelectronics laboratory of Professor Irfan Siddiqui. His research focused on strong light-matter interaction in superconducting quantum circuits. He obtained his BSc in physics from King Fahd University of Oil and Minerals, during which he worked on computational spintronics, doing, tight binding simulation of heterostructures. And today he's here, electronically here, talking about novel schemes of quantum control with strong light matter coupling. Ahmed, floor is all yours, so enjoy.
Great. Well, thank you for having me and for the nice introduction. I chose this broad topic, even though, okay, let's make sure the transitions are smooth. Yes, even though the bulk of my PhD work has been on what's called the Kirkat qubit, which requires strong light matter coupling, we've been recently trying to extend this scheme into other encoding schemes to enable novel operations. Okay, and with that, I'd like to start. This is the outline for the talk. So the bulk is going to be on the Kerr parametric oscillator, which we use to encode this exotic cat states of light and make qubits out of them. And at the end, I'll briefly talk about some preliminary results on translating some of this know-how into more traditional encoding schemes. Okay, and with that, what a better way to start than to celebrate the grandfathers of this field, who nearly 40 years ago showed for the first time that the superconducting circuit made with the Josephson junction gives you this, like inside this cosine potential, give you quantized energy levels. And by showing that for the first time and throughout like 2 decades of progress, people have been using this basic idea to encode quantum states and make quantum bits. And it's really fascinating. Like the field moved from like tens of nanoseconds in terms of the lifetimes of those artificial atoms, let's say, into now approaching the millisecond range with the novel schemes of encoding and improved engineering and material choices. And now the field is kind of mature enough at the level where the team at Google pretty much really managed for the first time to show that you can combine those noisy qubits, those noisy physical qubits into a larger logical qubit. And by increasing the surface distance, i.e. the number of physical qubits, you can make a logical qubit that has lower and lower error rate, which is the whole promise of quantum error correction, which is very exciting and tells you about the level of engineering the field has reached so far. I should also mention that there are also other platforms and many groups and companies that are investing in quantum computing outside superconducting circuits. And all of those platforms have their own advantages and challenges. But for the rest of the talk, I'll be focusing on this field of superconducting circuits. And so I really like this slide that I stole from Irfan on engineering an artificial atom. So this is the simplest circuits you can make with the Josephson junction that gives you the cosine potential. You can shunt it by a capacitor and make a nonlinear oscillator and use that as your qubit. This is commonly referred to as the transmon. It's been the most popular qubit in the literature. However, you can go rogue with your design choices and arrangements, and you can make like combine so many junctions, make loops, add leader inductors. And typically the challenge here is even though you make this sophisticated circuit more and more protected from the environment, it's also protected from the graduate student whose job is to control and manipulate this qubit. So there is this trade-off between protection and controllability. And so you don't want the student to be very frustrated. And For the rest of this talk, I'll be talking about the Kirkcat qubit, which instead of having the complexity added using the components of the circuit, we will shine light and make a nonlinear interaction between light and matter that gives us this kind of protection, but in a controlled fashion because we control the light. Okay, and so this is a nice scheme to talk about the Kerr parametric oscillator on the left and compare it to the common encoding of the transmode. They are all pretty much built using this cosine potential, which you can either engineer to have few bound states, but very large anharmonicity, i.e. the difference between the 0, 1 and 1, 2 transition, alpha. So you can make it as large as 300 megahertz and restrict your attention to 2 Fock states and use that to encode a pretty much an effective like a spin and a 2-level system in a qubit. On the other hand, you can make this energy well extremely deep and have so many bound states, and then this will look almost like a harmonic oscillator. And then you try to encode your information in a state that is superposition of so many Fock states. And so this is pretty much what we be focusing on, and then examining what are the benefits and challenges when doing so. And to realize something like cat states, it's really subtle. You will need very specific Hamiltonians and interactions to stabilize those kind of superpositions of high photon states. Okay, and with that, I'll like to review a few basic concepts for those who are not familiar with the concept of cat states. So cat states can be formally defined in terms of the semi-classical coherent states, the Gaussian states, that are basically the vacuum displaced by state alpha. And you can think of it as a state that has an average photon number equal to alpha squared. And the cats are basically those 2 states that are superpositions of so many photon number states, but with a well-defined parity. So there is either even number of photons in the cavity or odd number of photons. And those are pretty much the cat states. And the nice thing about the coherent states in this scheme is that they are pretty much quasi-orthogonal. So their overlap drops exponentially. And so the qubit itself will be defined pretty much by cat state along one axis, let's say the x-axis, and the coherent state along another axis, let's say the z-axis. And the other interesting property about the coherent states is that they are eigenstates of the annihilation operator. So if you are in the state alpha, you lose a photon, you're still in the same state alpha, which pretty much explains most of the properties when we make those qubits and how we control them, how we do readout, and how their lifetime is affected by the environment they live in. Okay, so now I'd like to introduce this slightly complicated Hamiltonian that I argue will be sufficient for us to stabilize those cat states. So the first term I show here is the self-Kerr or the kernel linearity of the oscillator. You get this for free if you have a 4th order linearity in your system. So you can imagine the system kind of spontaneously absorbs and creates 2 photons. So this is the Kerr oscillator. However, if your oscillator is also able to do 3-wave mixing, which is going to be the challenging part to realize experimentally, you can shine light on this oscillator, and it will absorb this high energy, high frequency photon that you shine and create 2 excitations at a time in your qubit. And that's pretty much the 2-photon drive that we want to realize, or commonly referred to as the squeeze drive. But here there is no squeezing, because in the presence of the Kerr, the 2-photon drive pretty much turns this nearly harmonic potential into this kind of effective double well metapotential. And we can see that by showing that a coherent state alpha is indeed eigenstate of this Hamiltonian, provided that alpha is equal to epsilon2 divided by k, i.e. the amplitude of the drive divided by the nonlinearity. So the intrinsic nonlinearity kind of the resistance against you populating the higher states, and the two-photon drive is pushing the system to populate the higher and higher excited states. And the other nice property of this Hamiltonian is that besides stabilizing two states, alpha and minus alpha, it also creates a gap between those two states and the higher excited states. So you can do operations and you restrict your attention to those two lower states and forget about the higher states. Okay, and the nice thing in this encoding is that now the annihilation operator and the creation operator pretty much on this new qubit that you define using the coherent states or the cat states act as a Pauli Z operator. Okay, great. So this is the 2D chip. It has a lot of components on it, but I'll only briefly describe one part, which is the Snellman oscillator. This oscillator where we have two large capacitor paths connected by an arrangement of Josephson junctions. And the rest is used to read out and control this qubit. So the really challenging part is to realize this three-wave mixing. And one way to do it is to have this arrangement of Josephson junctions that have this kind of effective potential that kind of looks slightly complicated. But the idea is, under some appropriate conditions of biasing, this oscillator will ultimately behave as a weakly anharmonic oscillator. So it has some frequency of the order 5 gigahertz, 6 gigahertz, and non-linearities here of the order few megahertz. So yeah, it will behave like a very weakly anharmonic oscillator. And the idea is now you can drive this Hamiltonian and do the appropriate transformations. And this will ultimately boil down to the Kirkcaldy Hamiltonian that I showed earlier. Yeah, so yeah, I think I'll leave it at that. Next, well, the question is, once you have those cat states, how do you confirm that you have those cat states? And there's been a really nice a protocol that pretty much uses the nonlinearity of this Snellman oscillator to distinguish if you are in the alpha state or the minus alpha state. And the procedure is fairly simple. You just drive this nonlinear oscillator at the difference frequency between the oscillator that hosts the cat states and another ancilla mode. And that activates a beam splitter interaction between the two. But because this beam splitter interaction is weak, you can pretty much treat A and A dagger as Pauli Z. So what this tells you, because you are in those kind of coherent states, you can take photons for free. And the photons you take will have a phase that depends on the state of the qubit. And that's pretty much how we perform the readouts for this qubit. So we ramp up the stabilization drive that creates the two metapotential wells. And then we drive at the difference frequency. And that populates an ancilla oscillator that ultimately decays away, and we collect this signal that comes out. And we see very distinct output states with a phase, a plus phase or a minus phase, that really tells you in which will the qubit was. And we can quantify how good this scheme is, like how well the Kirkcaldy qubit can give you photons for kind of almost free, by doing two repeated measurements and asking what's the probability that the second outcome is the same as the first outcome. And we get a QNDness as high as 99.6%. And so this is really a nice way to also initialize the qubit. So by doing this measurement, with very high fidelity, we can put this qubit in any desired state and use that for the rest of the computations we want to do on it. Okay, next I'd like to explain the lifetime. So if you have a single photon in the qubit, it can decay with some characteristic time t1. In our case, it was like 40 microseconds. However, once you start to build those cat states, their lifetime drops as you increase the average photon number due to the bosonic enhancement factor. So the basic idea is this annihilation operator, again, will look like almost a Pauli Z with an enhancement factor alpha. So in your master equation, the decay event will look like a Pauli Z error that's enhanced by alpha. And that's what we observe experimentally. The lifetime of the cat states drops as we increase the average photon number. So this drop is undesirable, but it's a property of the cats. The only kind of good thing here is that for those who kind of think about error correction and the kind of errors do you want to correct for, this is a photon loss or an amplitude damping error. However, due to the encoding scheme, now it translated into a Pauli error, which is much easier to deal with. So even though the output value is worse, the structure of the noise is kind of advantageous. But the nice thing about those qubits is when you don't look at the lifetime of the cat states, you look at the lifetime of the coherent states. So the coherent state is supposed to be eigenstate of the annihilation operator. So you can lose photons all you want. The qubit will not flip. Alpha will not turn to minus alpha if you lose photons. And it's kind of almost the case when we increase the average photon number here on the x-axis. You see the bit flip lifetime increases substantially from like 40 microseconds to hundreds of microseconds and almost approaching a millisecond. However, we have this weird staircase behavior that's not captured by this kind of projection trick that we have been employing for control and understanding the lifetime of the cat state. However, it seems the explanation lies in the structure of the higher excited states. So the lifetime of those states is really limited by an excitation that takes you to a higher excited states and then tunneling back to the states in the other well. And the idea, as you increase the amplitude of the drive, you make those wells deeper and deeper, so more and more excited states fall in. And once a pair of states fall into the double well, the lifetime shoots up and increases. So you have this behavior of staircase due to finite, nonetheless non-zero heating in the system. But nonetheless, we are able to achieve a millisecond bit flip lifetime of those kind of exotic states of light. Okay, next, it's typically the challenge when making kind of sophisticated states of light to make a qubit. You can gain in terms of the lifetime, but really suffer when you try to do logic operations. So how do you control those states? How do you convert a coherent state into a cat state? Typically, for a qubit that's encoded in like a 2 states, you can just do Rabi oscillations. And those Rabi oscillations enable you to have universal control, typically, for a 2-level system. Because you can drive with some phase that rotates you along X and a different phase, so you rotate along Y. But the cat pretty much suppresses this ability because the coherent states themselves now define a unique phase. So if you drive in the phase of the coherent states, you get an enhancement factor alpha. If you Rabi drive but out of phase, you get an exponential suppression. And so you can only do kind of rotations along one axis now. So another way to have universal control beside continuous kind of Z rotation is to at least do an X pi over 2 gate. And the scheme that was realized before relies on turning off the 2-photon drive or the stabilization drive abruptly for some amount of time. So the qubit only evolves under the kernel linearity. And it's really fascinating. You start in a coherent state, and now you can write your coherent state in terms of the Fock states, and they are eigenstates of the kernel linearity. And the system basically experiences collapse and revival of the coherent state due to its own self-curve. And so the coherent state will turn into an quote-unquote imaginary cat state, but along the y-axis and goes back and forth. So this gate is nice, but the challenge with it has been you turn off the stabilization drive that gave you the protection. So we don't want to do that. And later, in a few slides, I'll show you a different scheme that we introduced to implement this gate. So first, this is our data when we try to drive on a resonance, and we see this chevron. So if you drive in phase, you see very fast Rabi oscillations. If you drive out of phase, you see this exponentially suppressed rate. This is expected, and we can use this to pretty much calibrate kind of our gates to do, for example, an x pi over 2 rotation. And we can get very high fidelity with those qubits as high as 99%, which was nice. Next, yeah, so we would like to introduce another knob in this Hamiltonian, pretty much the detuning between the drive and the oscillator frequency. And the idea is you can introduce a negative detuning, and the effect of that is basically making this double well potential shallower and shallower. Basically, the drive is more and more detuned, so it cannot kind of populate the excited states. It cannot create this true double potential effectively. So we can use that to our advantage. Basically, introduce a controlled detuning. So we turn on the stabilization drive, and then we modulate it. We modulate its frequency. So by modulating its phase, it's effective to some detuning that we introduce. And that detuning basically make the well kind of shallower and shallower, allowing the two states to tunnel back and forth. And so this is kind of the calibration we did, and it's a very interesting gate. It's not a continuous rotation. It's a kind of a jump outside the block sphere and back. And nonetheless, the performance of this gate was as high as 95%, which is much higher than the previous realizations of the fidelities, like 90-something%. Okay. We can also, on the other hand, make this detuning on the opposite direction, which seems to make the wells actually deeper, and which helps stabilize more and more states inside the well. And so you can figure out how many states are inside the well by looking at the degeneracy of the excited states. So the ground states are always degenerate. And as you increase the detuning, you make higher and higher pairs of the excited states become degenerate, which means they are now inside the well. And so their contribution to the tunneling is minimized. And we see that influence on the bit flip lifetime. So we can fix our drive and just vary the detuning. And we see the lifetime pretty much approaching and exceeding a millisecond. Okay, next. Yes, a few comments on the noise bias of this qubit. So now we have made a qubit that's along one axis very, very protected, but along another axis, really fragile. But that turned out to be actually advantageous when you do quantum error correction in some sense. Like for a given error rate, having a high noise bias is in some sense a good thing, because now you know what are the dominant errors. And so you can dedicate your resources more towards that. And so here we are basically just, instead of just looking at the lifetime, which is, you can say, the fidelity of not doing anything, to the fidelity where I'm continuously rotating this qubit, applying this kind of Rabi drive. And this is pretty much the figure you can look at. Basically, we have a phase flip error and a bit flip error. So the bit flip error is when I have those coherent states that are not supposed to be affected by this Rabi drive. Are they affected or are they not? And the error rate is of the order 10 to the power minus 4, which is typically much lower than any single qubit operation in the literature. That's typically the standard in the literature, 10 to the power minus 3. But the fragile quote-unquote cat states are also experience a tiny amount of error of the order 10 to the power minus 2. And with that, we can conclude that we at least have some points in our system where, according to other theory work, would be within the fault tolerance threshold. So you can at least the single qubit operations are now with this kind of exotic cat states within this regime where, in principle, if you scale them in a surface code, they would show you exponential suppressed errors. Okay, and so yeah, this is the story of the single cats. And so the limitations here are, well, this is just a single qubit experiments. Can you entangle those cat states and do logic between them? And can you realize them with higher and higher nonlinearities such that you can do your operations faster and faster and have lower and lower error rates? And so this is kind of the two active research directions with those qubits at the moment. So this is the mask that we designed for the two qubit experiment, where we have two snail moon, quote unquote, oscillators that are capacitively coupled and very highly detuned, of the order 1 gigahertz compared to their coupling strength. And the idea is to use those two qubits to demonstrate a controlled Z-gate. And for those who are experts in the field, typically when you couple things capacitively, you would have a parasitic ZZ interaction or a cross-Kerr interaction. But here, because the nonlinearity of the system is really weak, the static interaction is extremely small. And because you encode your information in cat states, the cross-Kerr is basically telling you how many photons in this oscillator affects this oscillator. But the cats have the same, the Bloch sphere throughout has the same average photon number. So the photon number on average doesn't change. And so this interaction doesn't affect you. So that's a good thing to know. And so the task now to realize the controlled Z-gate is to realize this Hamiltonian. So all we need is a beam splitter interaction between those two oscillators as in single qubit drives, which again, if we remind ourselves that A and A dagger both simplify to a Pauli Z operator, this whole interaction Hamiltonian just boiled down to ZZ interactions between the qubits, which under the appropriate time evolution gives you the controlled Z-gate. So it's all like kind of a byproduct of how the encoding turns those bosonic operators into very simple Pauli Z operators. Okay, and so this is the preliminary results with those coupled snails. So what we can do as a first experiment is to excite, still work in the Fock basis, excite one oscillator, then turn on this drive at the difference frequency, which basically eliminate this excitation from one oscillator and put it in the other oscillator and back and forth. And that's pretty much what we see. When we drive on at the difference frequency, this excitation kind of moves back and forth between the two oscillators. So this is the beam splitter interaction in the Fock encoding. And in our system here, we can realize it with very fast rates of the order 100 nanoseconds. And so we look forward to how this would behave once we stabilize the cat states and try to make the control Z gate out of it. Okay, the other part, yes, is can we increase the nonlinearity of those cats such that we can control them very fast compared to their lifetime before we worry about leaking our states to higher excited states that we don't control and we would like to neglect altogether? And the answer lies in realizing efficient wave mixing. So maybe I'll go very quickly over this, but basically for a generic potential, you would have a quadratic term that gives you the will for the harmonic oscillator and higher nonlinearities that are supposed to be small. And so when you're trying to do wave mixing, like drive with a photon and absorb it and create your nonlinear drives, you can do it at different orders of the interaction. And so if you're trying to do wave mixing, a three-wave mixing, the simplest way is to do it by modulating the coefficient of pi square instead of having pi cube and modulating that. And that's pretty much the the idea we have been developing with our collaborator at Chapman, where we replace the snail by the squid. And I really like the terminology in this field. But the basic idea here with the squid is that you can realize your wave mixing at a higher order, so you can make both the kernel linearity and the two-photon drive much higher. And so you can make a cat that's much faster, which is advantageous. Okay. And so to put things into perspective, this is where we started with the snail and a harmonicity around 2 megahertz. And now we are operating at harmonicities around like 40 or so megahertz. So it's like between the transmon and what we realized so far, but an order of magnitude away from each side. Okay, so the first experiments so far, we were trying to first understand how things look in the Fock basis. So here we can, for example, prepare the first excited state, and we see the lifetime of like 48 microseconds, and then prepare higher and higher excited states and see their lifetime, and everything behaves like we expect. We just have bosonic enhancement factors. Next, we can, again, generate this two-photon drive, but if we make it weak enough compared to the spacing, you can drive the 0-2 transition in a Rabi fashion without populating the higher and higher excited states and making a cat. So this is what we see here. You can make a quote unquote a qubit if you wish, that's encoded by either no photons or two photons at a time. And we can see very fast Rabi oscillations of the order 80 nanoseconds in this oscillator. Moreover, we can try to engineer color dissipation. So what we can do, we can start in the third excited state of the system and then drive it at a difference frequency between this oscillator and an ancilla mode. And that ancilla decays very, very quickly. So if you are in the third excited state, you drive at the difference, you engineer this dissipation, and you end up in the second excited state. However, if you started in the second excited state, you turn on this dissipation, the 3-2 and 2-1 transitions are not the same in frequency. So the second excited state is not affected. So you have engineered a dissipation that has a very specific frequency. And so with that, we can try the following scheme for stabilizing states autonomously, or a form of optical pumping, let's say. So let's say you want to stabilize the system in the state 2, and it spontaneously decays to 1. So you can use your two-photon drive to drive it to 3, and use your color dissipation to bring it back to 2. And so with this, before the system decays to 0, you should be able to stabilize it in the states with 2 photons. And this is the data. So if you are not doing anything, the lifetime of the second excited state is like 27 microseconds. However, if you do those schemes of 2-photon excitation, the color dissipation, let's say every 10 microseconds, you see kind of the effective lifetime of this state is now like 260 microseconds, like an order of magnitude improvement. And as you do this and approach the continuous limits with smaller and smaller separations, you see this lifetime improves slightly. And when you do this correction every 2 microseconds, it goes as high as 500 and kind of 70 microseconds. And so you kind of really stabilize your system, which reflects the quality of how clean the microwave wave mixing. So when you drive those nonlinear processes, you only drive the ones that you care about, which is also, I think, exciting if we try to probe this further and maybe see if there is a structure to the decay event. So the dephasing of the qubits typically has a structure, and we can spin echo dephasing event on a typical qubit. But when it comes to T1, is the environment non-Markovian enough for us to reverse some of those effects when we do this kind of fast reset? All of those are open questions. And so, yeah, this is all kind of work in progress. Okay, next, this is the last part of the talk where we try to kind of take some of the lessons we learned from this Kerr oscillator and apply it to a more traditional encoding like the transmon qubit. So I would like to now stop and ask a slightly different question. Let's say I started with this transmon Hamiltonian. I have this cosine potential that I can expand and just reduce it to an effective kind of linear oscillator with a fourth order nonlinearity. And then I would like to drive it either through charge or through phase, kind of position and momentum. So if you drive it on resonance, you will just have Pauli X kind of and Pauli Y. Those two drives are really the same. However, what happens if I take my drive frequency and make it far detuned from the resonance frequency? Will those two drives still give me the same behavior? My first guess was the same. They would give me the same result, but in reality, it seems this is more subtle. And at very low frequencies, they behave differently. So if you drive it with the phase, you would have a very large stark shift. This drive would really stark shift your oscillator. But if you drive it with the charge, which is what we have been using with our snails and cats, when you go to low frequency, it becomes very quickly inefficient at wave mixing. It's like driving almost a harmonic oscillator at very low frequency. Nothing will happen to it in terms of the stark shift. And so this was a little bit puzzling, but it seems we can really understand the behavior of this kind of highly anharmonic oscillator using the language of the weakly anharmonic oscillator, where basically those two drives, very far off resonance, give you two contributions of rotating and counter-rotating terms that can add or cancel depending on the form of the original drive. Which was a kind of a surprise to us. And so this is just numerical results, but brute force. So as experimentalists, we wanted to go and make the chip and do the experiment. And so this is for those who have seen the transmon qubit, this is pretty much a transmon qubit where you have a capacitor that's connected using a Josephson junction. So we are not forming loops. We don't have squids. And so this is really the simplest transmon you can have. There are no tricks. The only change here is our line that we use to drive this oscillator is short to the ground. So basically there is a voltage node here and a current antinode. So you have a large current that can couple inductively to your qubit. And when we try to do the experiment, basically drive this qubit at very, very low frequency and ask what would be the stark shift on this qubit, we can see a very significant stark shift with a drive that's very highly detuned and very low frequency, which means this picture for the wave mixing happens and it happens efficiently. And so this is really exciting because I don't think this has been utilized before. And so what would be the advantages and the differences using this scheme compared to a typical squid where you modulate the flux? Okay. Moreover, this is another process that happens naturally. However, I don't think it was explored so far in the literature, but you have this oscillator and you have this four-wave mixing capability. So one obvious process is to drive it at 3 times its frequency and use this four-wave mixing capabilities to absorb this gigantic photon and create 3 excitations at a time. So this is kind of the Rabi oscillations where you drive this oscillator between the 0, 3 and skipping the 1 and 2 altogether in the process. And so this is the data, and we can really make this transition really fast, of the order like 15 nanosecond. So yeah, and now the question is, what's going on? How are we coupling to this qubit? And how is this inductive coupling happening? Without getting into too much details, it seems you cannot reduce the environment that Josephson junction sees into a capacitor. So these two pieces of metals are not just a capacitor, they are some effective transmission line, which has some self-inductance that's weak, but kind of large enough to mediate this coupling. And so this is an interesting surprise that even the simplest qubits in the literature has kind of different limits and properties that have been neglected so far, and can be quite useful to do different wave mixing processes. And yeah, with that, I think I'd like to conclude and thank everyone in our team, especially Benching and Kowang, and our collaborator at Chapman and Rochester. And thank you for inviting me.
Thank you, Ahmed. I think we have like plenty of time for questions.
Okay, great.
What are your questions, either from here or from the online audience?
Sorry?
No, I'm just asking if people have questions.
Okay. Yes.
I have a question.
Yeah, please go ahead.
So you mentioned the self-inductance on the capacitor pads.
Yes.
Is this self-inductance kinetic or geometric?
No, this is purely geometric.
Purely geometric.
Yes, yes.
Is it is it like currents that are being generated on the surface of this around the boundary of the conductor?
Yeah, so pretty much you can basically for example, when you excite using, for example, this port, you will see that the current you induce is indeed kind of circulating through each pad.
Right.
Because it's trying to shield the conductor from the magnetic field.
Right.
And yeah, and because of the kind of asymmetry between the structure of the pads and the structure of this loop, there will be kind of effective net kind of induced EMF across the junction.
Okay, thank you.
Mm-hmm.
Yeah, we have a question, other question here from the room.
Ahmed, you said the autonomous error correction for the double squid, right? So, I mean, do you need double squid for the autonomous error correction, or you can do it with the snail as well?
Yeah, very good question. So in principle, you can do it with both. The benefit of the squid is that now you are working in the Fock basis. So by having larger and larger anharmonicities, you can drive those states selectively without populating higher. So when you drive 0, 2, you don't push 2 to 4. If you had weaker nonlinearities, you would have to make this drive slower and slower, so you don't leak out. So to be able to, for example, show something like this, I don't think we would have been able to show this with the anharmonicity of 2 megahertz. And so, yeah, I think the large nonlinearity was really crucial to do those operations kind of fast enough and enable a resolution of the Fock states.
But since you are not stabilizing the cat state, why don't you have a large nonlinearity with the snail? I mean, if you are just looking at the Fock state, you can still have large nonlinearity with the snail, right?
Yeah, but typically, did I show you the tuning curve? Typically, the snail. Okay, I didn't show it here. But typically the tuning curve for the snail when you flux tune it is 6 megahertz to 0 megahertz. So this is with a double snail. With the single snail, you can get it up to like maybe 14 megahertz. So that's also a possibility. The other question is how clean the wave mixing is going to be. Like when you generate this 2-photon drive, how fast can you make it before it no longer looks like a clean Rabi oscillation? That's another property of the microwave hygiene. And as you probably know, with the squid, the microwave, like the terms that you can keep with higher orders in RWA are cleaner. So that's another difference. But yeah.
Thank you.
Sure. We have a question from the online audience, Gleb.
Okay, hello. I have a question. Do you distinguish between the coherence time and acquisition of information time? In other words, is there something in this measurement scheme which can mask through the coherence time, or you are in the quantum limit where acquisition of information time is equal to the coherence time?
Interesting. Are you talking about the coherent states that have very high lifetime? Are you referring to this trend? If I'd like to clarify before I comment.
Yes, probably it's about this.
Yes.
No.
Yeah. So basically, yeah. If I understand correctly, it's about the time scale for measurement and how that affects the lifetime of the states. And
yes.
Indeed. So, for example, typically after we do a measurement, we have to wait kind of long enough to make sure the system really relaxed to the ground state, such that we can repeat the experiment again. So that's typically dedicated by the lifetime of the oscillator itself, around 40 microseconds. So even if you are in a highly excited state and you wait we wait typically a millisecond or more. So even if you are in the 10th excited state or so, by the end of that time, you are pretty much close to the ground state. And moreover, even if you had residual population, we initialized this qubit using a measurement at the beginning. So even if you have a little bit of residual excitations in kind of quote unquote wrong states, the first measurement would really project you into either the desired states or the states you can neglect. And each time we do this measurement, we can select the few number of points that give us, for example, the state alpha, if we want to start in the state alpha, like here. And yeah, I hope that kind of answers your question.
It's a sort of post-selection or the state of you.
Yes. Yeah, we post-select using the measurements. So yes.
Okay, just because my impression from all the schemes, for example, for charge qubits, the time scales people measure as the coherence time scales or coherent the time scale of coherence.
You're also probably referring to how long the readout is compared to the lifetime of the state itself as well. So you can have a decay event while you're trying to read that.
Yeah, it's a story about the decay of Rabi oscillations. So if you measure something, you decohere by this measurement, and sometimes, for example, I don't know how about this transmon qubits, but for charge qubits, people measure acquisition of information time scale, which are longer than through the coherence time scale. That's why they can observe longer the longer time scale of the coherence when true
I see.
time scale.
Yeah, that might be a challenge if the acquisition time is long compared to the lifetime of the state itself you're trying to measure. But here we are in a totally different, like, kind of opposite limits, where, for example, how long is the readout versus how long is the lifetime of the state? Typically, the lifetime of the state, as I showed here, is hundreds of microseconds, almost a millisecond. And the length of this readout signal is few microseconds. And so if the readout was long compared to the lifetime, you can have decay events while you're still measuring. But that's not the case here, because our readout is really short and our lifetime is really long. So I think that's my answer.
Okay, thank you.
Thank you.
Okay, do we have more questions here or from Zoom? Okay, so let's thank our speaker again. Yeah, thank you, Ahmed.
Okay, great.
Yeah, thanks for zooming in.
Thank you for having me, and have a
Yeah.
nice day. Bye.
Bye-bye, bye-bye.